Hello, everyone. Welcome to this GGS webinar, which is our last webinar of 2025. Thank you all for joining. So today's a little bit different to our kind of usual webinar. So we're going to do kind of an introduction to ground gas for new professionals, and then we have a Q&A panel with JM, Andrew, and Heather. So do ask your questions using the box at the bottom of the Zoom, and we can get to those at the end. And I should also mention pretty shortly we will be sending out a CPD survey, which explores kind of different topics that you might be interested in learning about from us at GGS. So please do fill that in. It'd be really helpful to kind of understand what is useful for you. But I'll hand over to JM, who's going to run us through an introduction.
Thank you, Louis. Good morning, and thank you very much for joining us today for our webinar on an introduction to ground gas for new professionals. My name is Joao Dyer, and I'm the Managing Director here at GGS. And over the next hour, I'll be taking you through the following content. We'll go through what ground gases are and how they can become a hazard to a site. And then we'll go through some of the monitoring and risk assessment techniques. At the end of the presentation, we will have a Q&A panel where I'll be joined by some of my colleagues here at GGS, and you'll have time to ask questions, ask any questions you have. And please feel free to submit any questions as we go along, and we'll cover them at the end. But first, a very brief introduction to myself and to GGS. I've been at GGS for 14 years. I joined as a graduate a couple of years after GGS was founded, and then I progressed through the geoenvironmental consultant ranks. And now I'm the Managing Director following the recent retirement of our founder, Simon Talbot. I still spend a lot of time involved in projects, but now my role is primarily further developing our business and services to our customers. Despite focusing on continuous ground gas monitoring and risk assessment services, we've worked on a wide range of projects, which range from the Forth Road Bridge anchor chambers, major infrastructure projects, housing developments, which form a large part of our work, emissions monitoring services, landfill compliance monitoring, remediation compliance monitoring, as well as projects such as the dock redevelopment in Gothenburg in Sweden. All varied, but all ground gas related. So, what are the services we provide? Our core service is continuous ground gas monitoring, and we'd like to think of ourselves as the UK's market leader in providing this service and the associated risk assessment. We have also developed and continue to develop world-leading continuous ground gas monitoring devices. But we also carry out traditional spot monitoring of ground gases. We do surface emissions surveys, indoor receptor monitoring, groundwater sampling for dissolved gases and hydrocarbons, permit compliance monitoring, gas sampling and laboratory analysis, consultancy and peer review. So in summary, we provide a wide range of specialist environmental monitoring and risk assessment services focused around ground gas contamination issues. So that's the spiel over. Let's move on to consider the ground gas hazard. So while there have been previous disasters associated with ground gas issues, such as the fatal Abbeystead disaster in 1984, it was the LOSCO event in 1986 that changed the geoenvironmental sector. A public inquiry was held into LOSCO, and this was a catalyst for dramatic change in the understanding of the risks associated with ground gas contamination. A whole range of guidance documents was published following the public inquiry, which discussed the ground gas hazard, how to monitor and risk assess. And as a consequence, ground gas monitoring became a standard part of pre-development site investigation. So the LOSCO public inquiry identified the source of the gas as being landfill gas arising from an unlined landfill at the edge of a housing estate. The gas migration pathway was a fractured sandstone that dipped down under the houses of on Clark Avenue. And the receptor was number 51 Clark Avenue. So the source pathway receptor contaminant linkage now underpins ground gas risk assessments. But the public inquiry also identified a fourth factor that is unique to ground gas contamination, and that's a driving mechanism. And in the case of Losco, the driving mechanism was a dramatic fall in atmospheric pressure immediately before the explosion. The atmospheric pressure dropped by 27 millibars in the preceding 6 hours. This set up a differential pressure between the pressure in the ground and the pressure in and around number 51 Clark Avenue. This differential drew the landfill gas through the pathway and into the subfloor void. And at 6:30 in the morning, when the central heating system came on, a spark ignited what was an explosive mixture present in the subfloor void. But that was almost 40 years ago, and since then, there have been literally dozens of guidance documents published on the subject of monitoring and risk assessing landfill and ground gas hazards. However, there continues to be incidents and on occasion deaths associated with ground gases. One of the most widely reported events was the Gorebridge incident. This was a new housing estate which was designed and built for Midlothian Council in 2009. Then, in 2013, several tenants were overcome by gas and rushed to hospital, and the affected houses were evacuated. Over the following months, a total of 22 people were taken to A&E or sought medical help from their GPs. Because so many people had been affected, the local NHS Trust set up an incident management team in April 2014 to investigate the hazard. The team included the local authority, the NHS, and the coal authority. The cause was found to be mines gas arising from shallow mine workings beneath the site. It was decided that the best way of managing the problem was to demolish all 64 homes in the estate and rebuild them with effective gas protection measures. The consequence was also the demise of the lead firm of consultants that managed the original housing development for the council. The Gorebridge incident hit the headlines, but many ground gas issues do not. Often the developer and the local authority, understandably, quite quietly manage the issues out of the public eye to avoid blight or reputational damage. GGS knows this, as we have been involved in many cases, and as usual, we have to abide by our duty of care to our clients. So, there are a range of hazards that we need to consider. Explosive gases, such as methane, asphyxiating gases, such as carbon dioxide and nitrogen, flammable gases, oxidizing gases, toxic gases, carcinogenic gases, and vapors, as well as the naturally occurring radioactive gas radon. Now, some of these hazards are at percentage scale concentrations. Others, such as carbon monoxide and hydrogen sulfide, are toxic, and they're toxic at parts per million range. But we also have to deal with different timescales. So some of the hazards are realised almost instantaneously, such as the one seen at Losco, and these are acute hazards. Others take years and sometimes decades for the effects to develop, and these are chronic risks. So let's move on to looking at the key properties of ground gases. I'm going to use this schematic to demonstrate the difference between the three phases of potential contaminants. Take the first, this is solid contaminants, asbestos, for example. If we place asbestos in the ground, it will stay where it's put unless it's disturbed. Then liquid contaminants, they're predictable in that they will always flow down gradient. If you know where the groundwater flows, you'll know where the potential pollution plume will be. Now, gas contaminants expand and contract and can move in all directions and are much more unpredictable. Also, liquids and gases have very different viscosities. Air has a viscosity that is 50 times lower than water. This means that it can move faster and further for the same pressure driver. So let's move on to looking at the modes of ground gas migration. There are three modes, and the first is advective or pressure-driven flow, where gases move from areas of high pressure to areas of low pressure. This is what we saw at LOSCO. Then we've got diffusion, and this is a second mode of transport where the gas moves from areas of high concentration to areas of low concentration, and this occurs at the boundaries of former landfills. Now, both of these happen in the unsaturated zone above the water table. And the third mode of migration is below the water table, where gases are in solution, and here they will flow down gradient with the groundwater. So let's consider the diffusive and pressure-driven flow. This is a piece of research carried out by Ettinger and Kerfoot. They were looking at three different soil types: sand, silt, and clay. Now note that the vertical axes are logarithmic. The different coloured bars refer to different driving forces. So the orange represents the diffusive flow, and the other bars are different pressures, with the purple representing 1 psi. In the sand, which is a permeable soil, pressure-driven flow is 1,000 times greater or more powerful than diffusion. In the lower permeability soils, such as silt, pressure-driven flow is still 100 times greater than diffusion. So it's only in low permeability soils, for example clays, that diffusive flow is a more powerful driving mechanism than pressure. Now, a lot of consultants rely on modelling diffusive flow alone in their ground gas risk assessments. However, what we say is model if you must, but measure if you can. Moving on to another piece of research in pressure-driven migration. This is an early research paper carried out by Masman and Faria. They carried out a 2D finite element computer analysis on a very different model, on a very simple model, sorry. A box of permeable soil bounded at the surface and at depth with gases. A box of permeable soil was bounded at the surface and at depth, and gases were introduced to the left-hand side and exposed to a 25 millibar pressure fall over a 24-hour period. Now, with low permeability soils, silt or gas, like silt, the gas migrated 11 meters. In the fine sands, the gas migrated 25 meters. In the higher permeability soils, like medium sands, the gas migrated 45 meters. So there's a significant distance for an unusual pressure fall. Now let's turn to migration in the dissolved state. This photograph is of a stream, not groundwater, but as you can imagine, it's quite difficult to photograph groundwater, so this is just a bit of an aid memoir for you. So let's talk about the gas solubilities. At standard temperature and pressure, methane will be at saturation at 21 milligrams per litre. Is that a lot or a little? Unless you're familiar with this, you won't really know. So let's compare that to carbon dioxide. And carbon dioxide at standard pressure and temperature will be at saturation at 1,450 milligrams per litre. So that's 58 times more soluble. So it's this difference that I'd like to highlight here to give it relevance to those numbers. So to put this into layman's terms, methane doesn't like being in solution, while carbon dioxide loves being in solution. So the result is that if you've got landfill gas, which is a mixture of both methane and carbon dioxide, the carbon dioxide can be stripped out where it comes into contact with groundwater. And the further away from a gas source, the more modification of the gas composition which might occur. So let's move on and look at gas sources and migration pathways. Let's look at potential source risk factors. There are two elements that make a ground gas hazard: gas concentration, and gas flow rate. The gas flow rate is a function of gas generation rate, or the volume of gas which may be present within the source. A modern licensed landfill with processable waste will generate landfill gas at a rate of about 10 cubic meters per tonne of waste per year. Naturally occurring peat deposits will generate methane at over 90% concentration. However, the generation rate is very, very low in peat, and typically peat deposits will not provide a gas hazard despite the high concentrations. Now, the 23 former landfills in the UK have variable remaining content of processable waste and will have a wide range of landfill gas generation potentials. Brownfield sites, often in former industrial settings, may have a range of waste materials tipped or accidentally spilled, giving rise to a wide range of gases and volatile compounds. Here you'll need to look at the published industrial profiles to find out what may be present at a particular site. And finally, and often forgotten, 11% of the UK is underlain by coalfields. These have been extensively mined in the past and potentially give rise to large volumes of mines gas. So moving on to looking at pathways, I'm going to introduce some geological terms, specifically graded bedding and permeability and anisotropy. That's a bit of a mouthful. I'm still not sure if I've pronounced that correctly, but what it's describing is a naturally occurring characteristic of most sedimentary deposits. Each sediment or each sedimentary bed will have a fining upward sequence. Coarse material, coarse sands and gravels will be the first to be deposited from a stream. As current flow rates reduce, finer and finer sediments will fall out of suspension. So this gives rise to a dominant horizontal permeability compared to the vertical. Typically, the difference between horizontal and vertical permeability will be 100-fold. If the sequence includes silts and clays, it will be greater than 100-fold. So, putting this into context, this is a very simple schematic which shows a poorly sorted sand where the permeability is the same in all directions. Now, geologically, this is very unusual. What we usually find are fining upward sequences with permeability and anisotropy being a dominant horizontal, with providing a dominant horizontal permeability. And where we have a sedimentary bed that's capped by a clay layer, only horizontal gas migration is occurring. So we monitor ground gases in monitoring wells, which are constructed in boreholes. We often use these terms interchangeably, but it's important to recognise that these are two separate processes. A borehole is sunk to take soil samples, and a monitoring well should be considered a scientific instrument and needs to be both carefully designed and carefully installed. And this often doesn't happen. A properly installed monitoring well will have a number of key features. A response zone created from a slotted pipe and filter pack over the length of interest. This is sealed with a plain pipe section and bentonite clay, which creates a headspace where gases can collect in the well. And then the headworks at the surface to protect the monitoring well. So often groundwater will be present, and it's good practice to design the response zone so that it captures the unsaturated zone above the groundwater. Monitoring wells which have persistently flooded response zones are going to be of little use for a ground gas risk assessment. As we will see on the next slide, groundwater can have a significant effect on ground gases. So this schematic provides a potential problem with spot monitoring data, which we'll cover in a moment, where dissolved gases are involved and the gas risk is overestimated. Here we've got groundwater lying within the response zone, which is the slot or the dotted line of the well. Ground gases can freely enter the headspace through the response zone, where they can be monitored via the top valve. So let's take a situation where a low pressure system passes over the site. The atmospheric pressure falls, Methane, which doesn't like being in solution, degasses, and a small volume of methane builds up in the headspace. Perhaps the low pressure system is associated with heavy rainfall. Water might percolate down the water table, which rises. If the water rises above the top of the response zone, then the headspace will become pressured by the hydrostatic head. So if the spot monitoring reading is taken at this point, there will be a high methane concentration and a high flow rate. Oh, not too far. But neither of these issues, that the elevated flow and the high concentration, neither of them are a characteristic of the gas regime at this location. It's just a function of the geometry of the monitoring well and a small amount of degassed methane. Now, this schematic shows a number of sedimentary beds with the usual dominant horizontal permeability. The monitoring well's been sunk vertically through those beds. This means the monitoring well only picks up the horizontal gas flows, whereas most of our interest is at the surface where the development's going to be. New developments in most cases will only be susceptible to the vertical gas migration. This means that our monitoring will often overestimate the risk to that surface development and give us a conservative position. However, there is a significant caveat to this statement. Where we have ground improvement works, piling or site reprofiling, preferential pathways may be introduced. In this circumstance, our gas monitoring and risk assessment may underestimate the ground gas risks. Now, finally, the well itself may represent a preferential pathway. Monitoring wells shouldn't be located under the footprint of a proposed building of a new development. If they are, and often you can't avoid that, then if this happens, then you should effectively remove the monitoring well by over drilling and grouting. So we've looked at the sources and we've looked at the pathways. The communication tool which brings these together with receptors is a conceptual site model, as shown here in a schematic. If you want to comply with good practice and British standards, a schematic cross-section through the site must be included in the ground gas risk assessment. This will demonstrate the relationship between the source, the pathway, and the receptors. A CSM will inform where you should be putting your monitoring wells and allow you to effectively communicate to possibly non-specialist clients and contractors. And it's important not just to think about the location of the wells from a bird's eye view, but also, again, the response zone. It's depth and location that's critical. Now, the risk assessment process has a number of tiers. Tier 1 is based on a desk study and all the available information that you can get from historical data will help you identify whether there's a credible contaminant linkage in the first place. If this demonstrates that there is one, then you move on to your Tier 2 risk assessment. And this is a generic risk assessment based on, for instance, gas screening values, GSVs. Now, the Tier 3 is a detailed quantitative risk assessment. And the point I'd like to make is that whichever tier you're working on, you should use multiple lines of evidence to support your conclusions. For example, a ground gas risk assessment shouldn't just be the GSVs. Don't just look at the gas concentrations and the flow. And it shouldn't ignore all the site-specific issues which may reduce or increase the ground gas risk at the site. So look at the site as a whole. Don't just look at your gas concentrations and readings. Now, I'm going to move on to the monitoring techniques. We've got spot monitoring and continuous monitoring, and we'll have a look at the differences between these two. So the current best practice is encapsulated within a wealth of guidance, including Syria C665 and the Ground Gas Handbook. Many lines of evidence from a wide range of sources are drawn together, including monitoring data. This can be collected by discrete, periodic, or static measurements of monitoring well gas concentrations and flow, and this is what we call conventional spot sampling. In most situations, this might be adequate and allows appropriate design and gas management decisions to be made. But spot sampling data has its limitations as readings are taken in just a moment of time. It's just a screenshot or a snapshot of your site. The equipment that we use includes multiple multi-gas analyzers, such as the GA5000 here and the GFM devices. You've got single gas analyzers, such as photoionizing detectors, PIDs. You've got a Tiger and a Mini Ray here, and they do your total volatile organic compounds. And you've also got ppm range devices, such as the Crocon FID, or a flame ionizing detector. However, as the name implies in that there's a flame in the instrument, and it's not intrinsically safe and shouldn't be used in potentially explosive environments. However, there are other instruments like the TDL 500, and this is intrinsically safe and can be used in potentially explosive environments. And last and not least, a water dip meter. As mentioned just now, the changes in groundwater level can have a profound effect on gases in the unsaturated zone. So it's very important to be aware of where your groundwater is in your well. But whatever instruments you're using for your spot monitoring, the results from one day's visit will be recorded in a table. Similar to this one, and usually each parameter will be recorded in a separate column. You'll have pressure, methane concentration, peak and steady, carbon dioxide, oxygen, etc., and your flow. And each row will represent each monitoring well. And with each weekly and monthly visit, another table, and another table, and another. But there are a number of challenges with spot monitoring. Firstly, there might be transcription errors from what is recorded in your site notebook or tablet to the type table in your report, particularly in winter or when the weather is bad. Cold, wind and rain make site notes smudged and illegible. Was that a decimal point? Did I really record 70% methane, or was it 7.0%? Site tablets as well, they're great, but they can be difficult to use when it's very sunny and bright, or when it's raining, getting a response from the touchscreen. Secondly, interpreting page after page of tabulated data is tedious and time-consuming. And thirdly, you need a lot of readings to get a representative picture of the gas regime. This is particularly true if there's a lot of variability. So for a site where the gas regime is complex, continuous monitoring is extremely valuable. So the gas clam was the first generation continuous ground gas monitoring device. And since then, the technique and equipment have evolved, and we now have the gas sentinel, which is our second generation device. It's smaller, lighter and smarter than the gas clam. In addition to continuously monitoring gas concentrations, it also continuously measures flow. It's also telemetry enabled, which is particularly useful on longer deployments and can reduce the number of site visits that you need to do. In 2009, continuous ground gas monitoring was a sort of esoteric university spin-off technique. Now in 2025, it's widely used to provide high quality data in a short period of time to meet your regulatory requirements. So what is continuous monitoring? This is our definition. Monitoring carried out by an in situ device that records time series data at a monitoring frequency that exceeds the frequency of change of the measured parameter, which is typically hourly, for ground gases at least. So instead of tables of data, we have graphs, which show the full range of variation through time. And in this case, methane concentration within the monitoring well. However, the real value of the technique is by evaluating the relationship with environmental factors, looking at environmental correlations and identifying or eliminating correlations with atmospheric pressure, temperature, and groundwater level, or identifying or ruling out ground gas migration drivers. This slide shows one of the correlations we often see. Here we have captured a falling pressure event of over 20 millibars, that's the blue line, and the red line is the methane concentration in our monitoring well. Here we can see an inverse relationship with gas concentration rising as pressure falls. The maximum gas concentration only occurs at the lowest pressure. In this case, if you look on the bottom axes, if we were taking spot readings, you would need to take a reading at 4 a.m. on the 30th of December to get your peak gas concentration. Now, my colleagues like yours will probably be reluctant to do site work at that time on New Year's Eve. However, it's easy to continuously monitor. It's easy with continuous monitoring, as you can place it in the monitoring well and leave it to collect the data for you while you're back at site or back in the office or at home. The real value of the technique comes when we capture repeatability. So here we can see that every time there is a pressure fall, there is a spike in gas concentration. There is a direct correlation between the two, and we can have confidence that pressure is a key driver for the ground gas at this location. But it isn't always pressure. This is a former petrol station earmarked for residential development. VOCs were the contaminant of concern, and we found this relationship. So the VOC concentration is responding directly with the daily variation in temperature. The monitoring was carried out in August and September, and the sunshine was heating the soils and increasing the volatilization or free product present beneath the site. We have also observed a diurnal pattern in VOC concentrations inside properties, and these were caused by the use of the internal spaces and the associated ventilation, which meant that the VOCs were building up overnight and they were quickly dissipating in the mornings before we took our grab samples. So it kept missing the peak concentrations, because as soon as we entered the property, it was diluting those concentrations. The key driver, though, could also be groundwater. This is a proposed hotel on a redeveloped dockside site in Southampton. And the gas concentration here is directly affected by the tidal influence in the groundwater. You can clearly make out the neap and spring tides and the variation between the two. So what's happening here? We've got rising and falling atmospheric pressure, but the methane and carbon dioxide concentrations are flatlining at around 70 and 30% respectively. So this is landfill gas, and it's being continuously generated within an active landfill. The gas generation rate is independent of the outside environmental factors, so it's effectively kind of beating atmospheric pressure because of generation. You may know that the biochemical reactions within processable waste will always produce landfill gas at the fixed ratio of 60% methane and 40% carbon dioxide. However, there will always be some leachate within an active landfill. And as we discussed earlier, the leachate will strip out some of the carbon dioxide. So the carbon dioxide will go into the solution, into that leachate or groundwater. And in almost all active landfill monitoring locations, we find that landfill gas ratio is about 70 and 30% because of that effect of carbon dioxide going into solution. Now, this flatlining behavior gives us an insight into gas migration behavior. The closer you are to a gassing source, the more consistent the gas concentrations will be. And the further away you are from a source, the more variability and gas concentration modification you might see. Now, this is a slide where we have the key parameters recorded at the top of the graph. And in this case, it's pressure. We've also got borehole pressure there, which is quite closely aligned. Then we have the continuous concentrations of the gases of concern. And in this case, it was methane, which is in red, carbon dioxide in black, and oxygen in green. But it could also include hydrogen sulfide or carbon monoxide. Then at the bottom, we've got a continuous record of the gas flow rate. And you can see that there is, again, a correlation between flow and falling atmospheric pressure. So both the concentrations and the flow is being affected by falling pressure. I can't remember if I mentioned this on another slide, but if you think back to that effect we saw from the spot monitoring with falling atmospheric pressure and the water level rising, you can start to have an idea if that flow is real or representative generation, or if it's an effect of the artificial features being introduced by the monitoring well itself. So when is continuous monitoring useful? Well, when there's uncertainty. This is spot monitoring data that indicates that every time that readings are taken at borehole 1, we have high concentrations of methane, which indicate landfill gas migration, or you're in the source. We know we have a problem and action will be required. So continuous monitoring probably isn't needed in this situation. However, in this spot monitoring data set, sometimes there is methane present and sometimes it's absent, and the maximum concentrations might not have been captured. So in this situation, continuous monitoring will help to accurately characterize the gas regime at this location. And continuous monitoring can also be helpful when time is short. High quality data can be collected within just a couple of weeks, or a few weeks, 3 or 4. We often get called in by developers who failed to read the small print of their planning permissions, which required them to do a ground gas risk assessment before construction began. So they've got tight timescales to meet, and that's where continuous monitoring can help. Continuous monitoring is also helpful when worst case conditions need to be identified, such as those approaching the LOSCO situation. So we can be confident that we've got data when there was a big fall in pressure, and see if there was any response and if pressure is in fact a driver at that site. But continuous monitoring can also be used when the ground gas risk beneath an existing building needs to be quantified. So for instance, we can investigate the ground gases present within a subfloor void. We would look to capture the highest concentrations of gases within the subfloor void by measuring the exhaust gases through the downwind air bricks. This is a non-destructive test, and it's simple to carry out with our monitoring equipment, which can be securely bolted to the outside of a building. Normally we would install high-resolution sensors for this type of monitoring with sensitivities down to 0.025%. Again, it's important to consider the concentrations that will be important, and there's a big difference between gases in a monitoring well and gases in a subfloor void. And similarly, we can undertake monitoring inside buildings at suspected ground gas ingress points, such as your service entries. And again, it's important to consider how much gas in a service entry location would be significant. And finally, continuous ground gas monitoring can be used to demonstrate that the site has been successfully remediated. This was a proposed housing site in Scotland, which was affected by shallow mine workings and an adjacent landfill site. The site was remediated by reprofiling, which introduced placed and compacted continuous clay to remove the vertical migration pathways close to the surface. A representative number of shallow monitoring wells were installed into the clay, and continuous monitoring was undertaken to demonstrate that the ground gas risk had been effectively managed. Now, I'll leave you with some suggested guidance documents for reading if you haven't yet. Here we have BS 8576, which will guide you through the process for developing your ground gas investigation strategy. Syria C665, which provides guidance on how to conduct your ground gas risk assessment. And then BS 8485, which provides the framework for the design of adequate ground gas protection measures. Now, these documents provide the framework for your monitoring and assessment strategies, but aren't prescriptive for each individual site. So professional judgment also plays a key part in the decision making. So when you're doing your own monitoring and risk assessment, always record the justification for risk assessment and design decisions throughout the process. And this is another piece of guidance that came that was published more recently by EPG and Borough Happold for the NHBC. This document is easier to read than the British standards, and it builds on its earlier predecessor and stresses the need for professional qualifications and avoiding just-in-case gas protections. So also well worth a read. So that's all the slides. Now we're moving on into our Q&A session for this webinar. Please type in your questions in the Q&A button at the bottom of your screens, and we'll try and cover some of these. I'm hoping that I'll be joined by Andrew, our Technical Associate Director. We'll also have Heather Hodgson, our Operations Associate Director, and John Naylor, our Technical Director, all of which have a huge amount of experience with ground gas monitoring and risk assessments. So, Louis, I'll hand over to you to field the questions for us.
Thanks so much, Jim. Before we get started, should we just speak a little bit about the survey that we send out? So just as a reminder, if you weren't here at the start, we're going to be sending out a CPD survey, which is kind of asking a couple of different questions about what kind of content you want to see from us. We're about to start planning for webinars for next year. So it'll be good to kind of get your feedback. Shall I get started with a couple of questions that have been sent in by people who couldn't join the live webinar, then we can go through the Q&A box. Do feel free to drop your questions, as JM said. So first question, what are the key considerations when designing and installing monitoring wells for ground gas investigations?
Is Andrew or John there? I'll let them answer if they're there.
Yeah, sorry.
There's Andrew. What are the key considerations for designing a ground gas risk assessment? Was that the question, Louis?
Yeah.
Designing and installing monitoring wells, you said. The ground gas. Well, it depends on the gas source. Depends on your overall monitor objectives. If you're monitoring in a pathway or within or above a source, your design of your well would want to focus the potential pathways that you've identified in your preliminary CSM, and with focus above potential pathways in the unsaturated zone. Those are your key requirements. Obviously, the overall CSM is important in terms of the identified receptors. Yeah, I think that really covers that.
Yeah, I think the most common issue we come across is you'll have a great desk studies being done, highlighted all the issues and explained why there's a need for doing a phase 2 or a tier 2 ground gas monitoring and risk assessment, and then you find that all the boreholes have been systematically put across the site without being targeted.
So one of the key issues that we do see, is response zones that extend across different strata. So you might have a response zone that is within the sandstone bedrock, also within the glacial till and the limited made ground nearer to the surface. So it is difficult then to establish your dominant pathways if you do identify migration gas. Although consideration of all your lines of evidence will form part of your conclusions, but that's one thing to avoid, is to design the wells with that in mind.
Well, John's put his hand up.
Yeah, just to add on top of what Andrew's just relayed is obviously going your response zone across different horizons is not good practice. It should be avoided. I'm not a great fan of dual installations. I think you should have separate wells installed if you're going to do groundwater and gas, and again keep those separate. or clustered if possible. And third, think about the future. So if you do find gas, you've created a preferential pathway. So that actual installation might need to be later over-drilled and grouted up so you don't create additional trouble for the future development. So just watch out for those things as well.
Yeah,
Yeah,
often
absolutely.
they do get the assessments get completed and the monitoring wells get forgotten about. And then it's later determined that they do need remediating and grouting, and then they're lost.
Yep.
So the original ground gas assessment is no longer applicable.
Yeah, yeah. I think always going back to your desk study and having that next to you as you're designing your monitoring wells, not just looking at the final recommendation that monitoring wells are needed, but using the desk study to inform the design of them.
So
Thanks everyone. So next question, I'll move through the Q&A box just because we've got quite a lot here. So first question, with your series setup of the gas analyzer and PID, how do you make sure that the pull from the PID does not negatively affect the analyzer?
essentially, you set up in your tubing, you're taking a gas sample with your gas analyzer from the monitoring well, and the PID is monitoring the exhaust gases coming out of the gas analyzer and into the PID. You do often see some responses in there due to humidity in the tubing, differential pressures, etc. So it just requires some professional judgment when you're monitoring, but that's how you avoid negative pull, etc., affecting your strain on the instrument.
Would you suggest you doing that or doing it alternating which instrument to use?
It depends. I like to take a gas sample after your flow and measure take a PID reading at the end.
At the end, okay.
Yeah.
Yeah. I guess it depends. Like Andrew said, you need a bit of professional judgment to decide what you're trying to get out of your monitoring, but also be aware of the effects that having two pumps on the same system might affect each instrument.
It's essentially a screening exercise with your PID just to see what's there rather than taking the measurements as quantitative sort of face value. It's really to see what's there and to inform whether additional VOC vapor sampling is going to be needed to speciate those compounds if they are present.
Yeah.
Makes sense. And then Matthew is asking, what is the cost difference associated with continuous ground gas monitoring compared to spot monitoring?
Yeah, well, it costs more to do the monitoring itself, but the main win is in the savings, the subsequent savings, because you'll have a much better informed assessment. It removes the need for conservatism on your assessment because you'll be much better informed. You won't just be relying on gas concentrations, and you'll have much better decision making. It depends on the site as well, because like we said, with continuous monitoring, you only need one visit at the start and one at the end. Whereas if you've got a site that might be quite far to get to, if you've got to do 6, 7 or 8 spot monitoring visits over the course of 3 months, that in itself might have a cost, even if it's not a tangible financial cost. Time as well as the effort can be a cost. But typically where we find is that the savings, and they can be very significant, is on the subsequent work. And I appreciate that's very hard to communicate to your client who wants you're trying to compete with another consultant over the monitoring work, and obviously a higher price one will be difficult to explain. But I think that's where we try and communicate that it's the long term can create cost savings.
The quality in data and the how it informs a risk assessment, but also continuous monitoring with telemetry can be monitored remotely. So when you know you've got enough data that any additional data won't change that risk assessment, you can monitor that remotely and determine whether those instruments can be collected.
Yeah.
It's another advantage. You can also understand the gas regime in much higher detail.
Yeah.
Quality data set.
Perfect. And then another question from someone who couldn't join. So I know we've done a couple of webinars in the past on atmospheric pressure, but they would like to know how atmospheric pressure changes influence ground gas migration and what monitoring strategies best capture these effects.
Andrew's the expert in atmospheric pressure.
I would say that, but well, essentially, it's the application of continuous monitoring time series data to measure both parameters simultaneously. Measuring pressure, as we've seen, is quite established. Atmospheric pressure does influence gas emissions at the surface. It affects gas migration through geological pathways, and it kind of influences gas ingress into buildings. So it's key parameter to measure and understand in most ground gas risk assessment. Doesn't always affect the ground gas behaviour. Often it's not relevant at all, but often it is relevant. So time series data really is key for that understanding and to capture potential worst case conditions.
Perfect. And then kind of moving on from that, an attendee is asking if there are any other lines of evidence which are commonly used apart from spot monitoring and continuous gas monitoring for risk assessments.
John or Heather, want to take this one?
I mean, I can, but Heather, please pop in with a few suggestions afterwards. Yeah, there's loads you could do. I mean, we've just looked at 2 techniques of looking at borehole monitoring, but you could do all kinds of surface emission surveys. You can use different kinds of probes in the near surface soils for various activities, just to show whether you've got anything in the near surface soils. There's a few other things as well, just looking at the soil profiles, looking at the waste, or not even waste, but any sort of materials that are potentially gassy, and look at whether the gas potentials from those, and do more of a qualitative assessment on those, using total organic carbon, for instance, when you do soil sampling, to give you a feel for that kind of potential. There's modelling. I'd be very cautious on full modelling, because the ground can be very, very complicated. And of course, when you add buildings and infrastructure and all the sort of service trenches, that becomes even more complicated. So make sure, if you're going to model, make sure you've got enough safety factors of safety involved, as well as confirm your model with collecting evidence and data that shows that it's realistic in the application if you're going to do that.
Also key is dissolved gases as well. We often measure dissolved gases, and specifically I would look to measure dissolved gases when we have got a relatively high water table or a variable water table and a significant gas source identified. Usually it doesn't present a risk at the surface and degassing, but it can do in some situations. So a good understanding of the levels of dissolved gas is often key to update the conceptual site model.
Yeah, and I'd just add your CSM as well, that it's not just about the monitoring data, it's about putting that all together with your actual site. Sometimes you can have a lot of gas, but it's at depth, and what does that mean? Is it meaningful for the development that you're putting it on? So not just looking at your results in your data, but actually seeing what that means for your site and putting that together in one
whole story, not just looking at numbers.
Heather, can you add about potentially you do a lot of our VOC stuff and about sampling for that? Can you add any points on that aspect?
Yeah. We do quite a lot of laboratory sampling. So utilising things like 10x tubes, silo canisters. So you can either deploy them in a big range of different locations. They can go into vapor pins in the ground, so like stainless steel probes. They can also be used in boreholes. You can do active sampling of boreholes, passive sampling, and then also as well for internal sampling. Yeah.
There is another question actually, just to quickly answer, about using vapor pins. Like, what are your thoughts on measuring VOCs using vapor pins in the ground slab rather than a monitoring well?
Who wants to get? Shall I get that first? I mean, it's a well-established technique, and it's come across from the USA. Is it good? Is it bad? I think there's different opinions. We've used it in the past. It can be quite useful. Remember, of course, it is destructive, so you're having to drill holes through the slab. And if there's gas protection in there, such as membranes beneath it, you might have to reinstallate or think about how to fix those holes once you've made them. The other one is, of course, making sure that those vapor pins are sealed correctly and installed correctly. So you do have to do certain tests to ensure that there's no leaks. Easiest ones like what we call the water bath test, where you basically install your pin, you put cap on it, and then you basically put a little cap around it, fill it with water, and make sure it doesn't dissipate down the hole or reduce its leak. So they're fine. You can put caps on them, and they do give you some different information.
Yeah, I think it's key is the installation. Often below the slab might be quite low permeability ground as well, and sometimes I've seen occasions where they don't extend through the slab as well. So yeah, it's the checks that are key to ensure that they are fit for purpose, and the results are going to be reliable. But also, I've seen a question here: when you have negative flow values, what should you do when it comes to calculating CS value? Well, depends what's creating the negative flow, whether it's representative in your CSM that you developed. Often we see negative flows that are entirely a function of either ground water movement, the piston effect. We get a pressurized well due to ground conditions, and when you release the valve and measure the flow during the spot sample, that pressure then recedes, which creates a negative flow. So it depends what's creating it. Obviously, if it's relevant to the gas regime, then it can be considered, but often it's due to the well geometry and low cohesive, low permeability strata that's really affecting the flow measurements. I hope that answers that one.
Thanks, Andrew. Should we take a couple more questions, and then we can head off?
Just to add on the negative flow, with continuous flow measurements, you don't get the same response as you do with periodic monitoring. So that's one added benefit, because the instrument is being to take the measurement. It opens up the aperture to atmosphere every hour. It doesn't allow. It's less receptive to ground conditions affecting flow measurements. It does occur. Obviously, you need to review the data, and interpretation is key. But with spot monitoring, when the wells are left for weeks on end, that tends to be, something that happens quite regularly. It's often the ground conditions.
Yeah.
John?
Yeah, and just to add, that's within the British standard about unrepresentative flow rates.
Yeah.
You've really got to consider the data you're collecting and does it fit with what's going on, and when you can justify it, remove the silly spurious flow rates caused by the conditions of the well and the geometry.
Yeah, and you'll often see it in wells installed into the ground, but you've got the hard standing as well, so you haven't got that connectivity with atmosphere to the response zone. You've got the surface is sealed quite effectively, so you often get flow rates due to that, and it's just specifically down to the design of the monitoring well and the site setting.
There's actually two questions that are kind of similar questions, which is about horizontal migration. So kind of revisiting, going back to it, and why when should it be considered a concern?
Yeah, I've been having a look at those. Yeah, I think I'm trying to think trying to work out what the.
Well, essentially, if there's anything, a preferential pathway within that lateral migration pathway, obviously you've got the borehole, but it's relevant if there's at any point that ground gas can affect the site surface, whether that be through ground fractures, service trenches, groundwater movement, just to name a few.
John, have you got your hand up?
Yeah, just to add, when you come to lateral migration, continuous monitoring is pretty much the thing to use if you're going to spot that. It's very difficult to catch the full extent of migration otherwise with traditional methods. But on top of that, obviously, is placement of your locations to monitor. So again, back to your desk study, back to your site investigation, design strategy, and make sure that's considered in line with what you're attempting to answer, trying to do.
Yeah. And with distances, that's a hard one. Again, it's always down to this very site-specific situation. We've seen some sites where you'd expect there's a very plausible pathway, but it's so big that the gas is dilute within it anyway, and that's part of it. There might be other sites where the pathway's quite small, like a fracture in a rock, and that actually makes it go a long way because the rock itself is impermeable, but the fracture isn't. And then you can get quite long distance migration. I think we had that in a site in the West Midlands about a year or two ago. So it can vary dramatically. I wouldn't ever suggest putting a blanket figure on how far migration is. Obviously, will be eventually a top end to that, but whether it's 50 meters, 100 meters, or 200, it's very hard to say unless you know the site specifics. And regard the question on the horizontal migration, yeah, I think, John, you've kind of covered that a bit with, I think the important thing is to make sure where your well is and the response zone, because what you don't want to report in your site is that, oh, you've got X amount of methane at this location, when actually it's beneath 5 to 10 meters of clay and you're capturing migration that's happening deep, but not going to affect your development. So again, you can reduce your risk of capturing unnecessary horizontal migration by targeting the correct strata. But by all means, you can have one well targeting that, but then have another one showing that that's where it's limited to, and that it's not going vertically. So again, it's using multiple wells to prove or to demonstrate your case as to why you think that's the case.
As long as you don't then breach that nice clay layer with some nice permeable pathways, such as certain types of piling.
Yeah, exactly. And your monitoring well that you use to do it, grout it back up afterwards. Yeah.
Perfect. Should we take one more question and then leave it there? So got a question about kind of small sites and risk assessments. not kind of being up to scratch. So what is the kind of answer for this? Stephen would like to know.
Yeah, I think we've there've been there's some very small developments where someone wants to put a conservatory on their house and they're within 250 meters of a landfill. So one of the planning conditions is you need to do a full-on ground gas risk assessment. And yeah, for that it can be over the top in a sense, because sometimes the whole desk study, monitoring, risk assessment and remedial measures are going to be far more than the cost of a conservatory. And again, there's no blanket answer for it, but there have been some situations where we've just, if we know that there isn't an unacceptable risk, so there are already houses there that have been there for 80 years and the source is considered low to medium risk. Sometimes it's better to advise just go straight to the remediation strategy and put in a membrane, because it's going to be cheaper than working out that you don't need one anyway. That's on very specific sites where that might be better. But there is a bit of pragmatism that's required. There are other sites where there are small development, 2 or 3 houses want to be built, and it's a small scale builder. They haven't come across ground gas before, and typically that's when we get called in after everything's in place, which I can appreciate. That's probably where Stephen's coming from, where there's poor ground gas risk assessments have done. And again, yeah, on a small site, it's hard. The bigger the site, the cheaper the work is per plot, effectively. So when you've only got 3 houses, you can't do 3% of a risk assessment compared to a plot with 100 houses. You still have to do a desk study. You still have to do some monitoring. You can't, do one well. I think the point we make here, you still need enough lines of evidence to provide an accurate picture. And it's hard to meet that, and that we do try and be a bit pragmatic with that and not kind of make it economically unviable to do the work. But there's a balance between the cost and the safety. We still need to make sure that whatever conclusion our risk assessment has ultimately protects the receptor. Yeah, I'll let others talk. Sorry, I've talked a lot.
Now, I think just the only thing I could really add to that is for the smaller sites, again, a good preliminary risk assessment can help. But actually, just go speak to the regulators. They might know a lot more about that site than you do, and just see what their feel is for it. They might have investigations done in nearby. Doesn't mean it's bulletproof, but yeah, I completely agree. There becomes a cost benefit kind of calculation to do with their very small stuff, whereby housing already exists. If you put in a CS3 type protection system with ventilation and don't compromise what's already in the building, should be enough. And would, maybe a bit of post construction monitoring, but generally speaking, it is a grey area and difficult to justify the costs of full on investigation and risk assessment.
Often in those situations, the where it falls down is the QCA, CQA process, and the installation is often not fully understood or could be relied on. So that's, if you've got to put in gas protection, put it in right.
Yep.
Essentially.
Yeah.
Even when you feel that it's not required, or yeah.
Perfect.
You can't rely on it. You have to do then some expensive monitoring to prove that it wasn't needed in the first place. So you're back to square one.
Thank you, everyone. So I'm aware there's a couple of questions that weren't answered. So if you do have more burning questions after this, you can always reach out to us. But in terms of looking back on the slides and stuff, so the recording will be made available afterwards. And yeah, just again, keep a lookout for the CPD surveying, kind of the webinars that are coming up in 2026. But yeah, thank you for such a great presentation, JM, and thank you to everyone on the panel as well, Andrew, John, and Heather. And thanks for everyone who joined.
Yes, thank you.
Thank you all.
Thank you.